Strap in, ladies and gentlemen. AS Physics. I am going to give you an unbelievable understanding of this subject. We're going to go in here. Not only are you going to be able to do ace these exams, practically understand the questions, how to answer them, how to understand the theory, but we're also going to give you a deep and profound understanding of this subject, because without this subject, all of the modern world wouldn't exist. This is the birthplace of modern culture, modern society, modern thinking, and even your current experience of reality. This isn't a joke. This is a seriously important subject. This is our magnum opus, our holy grail. This is humanity's holy grail. This is the best thing, the most powerful, influential thing we've ever created. So I'm giving it the utmost respect here in teaching you this, because I'm assuming this is the first time you're properly being introduced to the subject. So I'll be giving it absolute respect. Without further ado, let's do it. Basically, we're going to be starting off with physical quantities here, and I've made a worksheet for you. But before I go through that worksheet, real quick, I just want to show you, okay, so I have these two other worksheets, or just pieces of digital paper, which have all of the relevant definitions that you're going to need throughout this paper. I'm not saying you have to know these right now, but I thought it'd be useful to have them all together. So you've got all these definitions here because they like to ask definitions a lot. And so you can also get an idea of what's to come. So you've got all the relevant definitions. I found this online. And also I found this sort of, I don't know, exam collection of all the equations and key concepts that you need to know as well, made by some guy ages ago. But you know, physics doesn't change, and I'm not trying to reinvent the wheel here. And so these are all be perfectly relevant, and so it's all there for you. I would recommend you download that just so you have it in a place. But we're going to go through all of this stuff anyway, and they'll all be in my own worksheets, but I thought it'd be useful just to have it all in one place. So yeah, I'll put those in the links in the description. Okay, so physical quantities. Pretty important, physical quantities. We have a physical world and we want to quantify it and understand it. I'll go through the theory in a minute, but basically I've extracted past paper questions for all of the times that they ask on definitions, basic definitions from 2018. You have all those there. It might be useful to do this part at the end of the exam hack series, but they're all there, and you know, I've written answers for all of them, but just thought it'd be useful because they ask definitions, basic definitions a lot. So, you know, they're only usually worth 1 or 2 marks, but they're all there. And then we have the physical quantity question, which is what we're going to be tackling today. This will be involving, you know, our SI units, our uncertainties, errors, vectors, scalars, these kind of things. I'll go through the theory in a minute, but I extracted all the answers for all the questions for this from 2018 to 2022, so 5 years. And you've got all of my written answers there on this worksheet. Yeah, so it's all there. So download that and you can go through and get an understanding of this question, how they like to ask it. All right, let's do some theory. Okay, so start off, prefixes. So there's these things called prefixes, which we use in physics to basically just symbolize big or large numbers. So it's pretty simple. It's just like, okay, milli. So 1 milli is 1 times 10 to the -3, or 1 micro would be 1 times 10 to the -6. It's just a symbol which represents either large or small number. It can be useful. You just kind of have to remember them. That's it. And base SI unit. So SI unit is basically the smallest, not smallest, the base quantity which we use for things. So mass would be kilogram. We could use pounds or something else from that, but the thing that we use, which all agreeing within science, is we're going to use kilogram here. And so for length, it's meter, for time, it's seconds. And you can construct units from all different types of quantities that you get. So for example, if you get a force of 10 newtons, well, that can also be written in SI base units. So you could write that in kg, it would be kg meters per second squared. Right? I'll show you how to do that. But yeah, so you can write all the different kinds of quantities in these SI base units. It's pretty helpful. We have scalar and vectors, so all of these different physical quantities can either be a scalar or a vector, meaning a scalar is just something that has magnitude. For example, something like temperature. The temperature has magnitude, but a vector, this has both magnitude and a direction. So we couldn't say that the temperature has, it's not 10 Kelvin to the left. That doesn't make any sense. It's just 10 Kelvin. It doesn't have a direction, whereas something like velocity, it's important that we specify its direction. That's because it's a vector. It's moving at a speed of 10 meters per second that way. And finally, we have these errors and uncertainties. So whenever we make measurements of reality, we get errors. We can have errors. This can be due to ourselves, like human errors, or the actual equipment that we're using. And for uncertainties, so you can read through that. We'll do questions on it. And for uncertainties, well, when we make a measurement, we can be uncertain about it. I mean, we always will be uncertain about it. We can't be 100% certain about anything that we measure because there's so many different factors involved, even in a simple measurement. Even measuring something like length, there's going to be an uncertainty. And that'll be, so, okay, it's 10 meters plus or minus 1 meter. So the plus or minus part is how uncertain we are. And so for plus or minus 1 meter, that would be called absolute uncertainty. It's in terms of the actual unit which we're measuring in. Whereas for the percentage uncertainty, well, that would be plus or minus 10%. And we can combine these uncertainties when we're finding a different set of data. So, I don't know, we have mass and acceleration. We have uncertainty values for these. Well, then what's the uncertainty value of the force, which is mass times acceleration? We have ways of calculating that, and I'll do a question on that as well. But that's basically all we need to know. You can read through this, and you also have this here, where you can read through these things as well to get a better idea. I will be doing questions to reinforce this information. Complete the table by ticking the appropriate column indicating this quantities are scalar or vectors. Okay, well, acceleration, is that a scalar or a vector? Well, let's have a look at it. Well, acceleration equals to change in velocity over time, so it involves velocity, which is a vector. So acceleration has a direction. So yes. Density. Well, density is mass divided by volume. Density is a property of the object itself. So really to understand, I mean, it's going to be a scalar, but to understand these things, you need to understand what these quantities are describing. Temperature, I talked about that a little bit before, but temperature, temperature doesn't have a direction. Momentum, well, momentum is mv, which involves velocity, which is a vector. So momentum does have a direction, so it's a vector. Cool. Use an expression for work done. Well, work done equals force times distance or displacement. In terms of force, I'll show the SI base units is this. Okay, so force equals mass times acceleration. So the base unit for mass and this acceleration equals to, change in velocity or velocity over time. Right, so for mass, the base SI unit is kilograms. So we're trying to get this thing into base SI units, because usually force is just written in newtons, right? So kg, and then acceleration is, well, change in velocity over time. Velocity is meters per second divided by time. That's just meters per second over time, which is second. And velocity is distance over time, right? Meters over second. So this is just meters over second squared. So this here is the SI base unit for force, and force is work done as force times distance or displacement, which is meters. So work done, which is force times distance, displacement, well, this is going to be in base SI units, kg meter over second squared, multiplied by, well, what is distance? Displacement is, or displacement is measured in meters. So meters. So it's going to be equal to kg meter squared over time squared, which equals to kg meter squared. We take this up, it just becomes a negative. That's what they have there. So that's the SI base units for work done, energy. So the energy stored is, so this is, okay. So Q is the charge, so Q, these are all equations which we will introduce later on. That's why I put those two general worksheets with all these together, because we're going to need them later on. But we'll learn later on that charge is current times time, and current is a base SI unit, which is amps, time is seconds. So charge is amp seconds. Use this equation in the information term the SI base units of C. So we rearrange this equation for C. So if we rearrange for C, we'll get times UC times YC divided by this, so it'll be just this. So we rearrange it, 2E. Charge, we have it in our base SI units. Remember, this is just all from here. So electric current, amp. All right, amp seconds. And energy, we found before from our work done, is this. So this is going to be equal to, charge is squared divided by this, which is our energy. And 2 doesn't play any factor into it's just a constant, so it doesn't have anything to do with our units that we're going to get. So this is going to be this divided by kg meter squared divided by this squared. So we're going to get a squared s squared over kg meters squared over s squared. Okay, so using a bit of algebra, this is going to be a squared, this will be s4 kg meters squared, and written like this, kg -1 m -2, sorry. So this is the base units for this C constant. A squared, amps squared, time, the 4, which is seconds, kg -1, 2. Measurements of a constant current in a wire are taken on an analog meter. For the measurements, describe one of the possible causes. Okay, so this is just understanding of definitions. Random error is something, usually, I'd say, or we can always say it's going to be some sort of human error. So this could be, just say, human error of like incorrectly reading this, or reading it at an angle. So we read the ammeter or whatever we're reading to take a measurement, but maybe we're looking at it not straight on, so it looks different. So it'd be incorrectly reading the ammeter. A good example of this is taking readings at different angles. Taking readings different angles. Systematic error is then something to do with the equipment itself. So a good example of this is the zero error. So we've wrongly calibrated the ammeter. So when it shouldn't be reading any current, let's say, well, then it's not 0. It's maybe a little more. So we can just say incorrectly calibrated. Yeah. Also known as zero error. Zero error is a good example of this. So you just need to go and read these definitions and understand them. In the following list, underline the units that are SI base units. Yes. No, this is force, but this can be written in SI base units. Degrees Celsius, no. It also can be written in SI base units. Degrees Celsius is not the base unit for temperature, it's Kelvin. And amp is. For those two. Okay. We have the stuff. The Young's modulus of the material is this. Okay. Where M is the mass. So the mass. M is the mass. T is the time of period, and K is a constant. We have these uncertainties in percentage uncertainties of each of these values. So this will show us about combining uncertainties. Okay. So the actual value of this thing is this. Calculate the percentage uncertainty of E. Well, when we times things together, we simply add the uncertainties. And when we take something to the square, this is just rules that you're going to have to learn. I'm sorry, it's just the way it is. When you take something to the square, or you just times by whatever it's squared to that the uncertainty. You see what I mean in a minute. So, E. So for dividing and timesing, we have this uncertainty. So we have an uncertainty here. It's just going to be the percentage uncertainty of E is simply going to be the percentage uncertainty of K plus that percentage uncertainty of M divided by 2 times the percentage uncertainty of T. It's just the way you do it. It's going to be 2.1% plus M percentage uncertainty 0.6% plus T, because it's squared, this would be 2 times 1.5%. It's just a method that we use. So when we are dividing and timesing, we add percentage uncertainties. Throughout the entire worksheet, you do that over and over again. Something you have to remember. So this is going to equal to 0.1 plus 0.6 plus 3. It's 5.7. So the percentage uncertainty for E, which has the relationship like this, was found by the individual uncertainties of these quantities which make calculate E. 5.7. Right? Use your answer to determine the value of E with the absolute uncertainty. Okay. Use your answer in BI to determine the value of E. With an absolute, so appropriate significant figures. Okay, so the absolute uncertainty of E is just going to be the percentage uncertainty times our value. Right? So our value of E is 8.245 times 10 to the 9. This thing multiplied by 5.7%, which is 0.057, equal to 8.245 0.057. So this is going to be 0.47 or 469. To a reasonable uncertainties like 1 or 2 significant figures is usually good. So we can just say this is 0.469 5. It's fine. But then we have to have this the same amount, so this would be 8.2. So this is all times 10 to the power of 9, 0.5 times 2. This thing is going to be 8.2 plus or minus 0.5. This is the absolute uncertainty. Right? This is the percentage uncertainty of 5.7%. Okay, a solid sphere has a diameter of that and the mass of this. Calculate the density of the material. Well, density equals mass over volume. And the volume of a sphere is 4/3 pi r cubed. Okay, so this is going to be m over 4/3 pi r cubed. And the diameter is this. So that means the radius will be half of this, because this is the value, right? This is the uncertainty, the absolute uncertainty in this case. And so this will equal to the mass, which is 67 grams. But we want it in kilograms. Oh, actually, no, we don't, because it's in grams already. So you do want to be checking the units. If it didn't specify, then I would have put it into kilograms. Okay, but it wants it in grams, centimeters, -3. So we'll keep it in grams. 67 grams divided by 4/3 pi of r. Well, r is just going to be half of this, which is the diameter. So 3.42 divided by 2, 1.71. 1.71 to the power of 3. This gives us times 4 divided by 3 times pi, and then 67. Awesome. So you get 3 point, rounded is 3.2. 3.2. Okay, and then determine the percentage uncertainty in the density. Okay, so we have the formula for density, similar to what we were doing before, but now we have these things in absolute uncertainties. So let's find the percentage uncertainty for each of these quantities which make up our density. So we have the percentage uncertainty of the diameter or radius. So radius, percentage uncertainty of our radius, or diameter, I guess would be easier. Because diameter equals to radius equals to diameter over 2, right? So the percentage uncertainty of our diameter is just going to be 3.42, 0.02 absolute uncertainty divided by 3.4 times 100. Divided by 3.42 times 100. So 0.58, 0.58%. And the percentage uncertainty for our mass is going to be, well, 2 divided by 67. 2 divided by 67 times 100. 2 divided by 67 times 100. Rounded is like 3%. Okay, so therefore the percentage uncertainty of our density, well, density equals to mass over 4/3 pi of diameter over 2 cubed, right? So we have a, this, all of this it's just a constant, doesn't do anything to our uncertainty. It's just times, we times something by a constant, it's not going to change the uncertainty, right? So we've got a d cubed and a mass. So basically, things that we're interested in is this. We have a mass on the top and a d cubed. So the percentage uncertainty of our mass was 0.58 divided by, so we plus d cubed. So this is going to be 3 times the percentage uncertainty of oh, the mass was 3. All right, my bad. It's 3% times 3 times 0.58%. Right, we're just times again. These are just rules that you have to learn. When we divide or times, we add percentage uncertainties. 3 times 0.58 plus 3. So this is like 4.74. So 4.74. It might be something to do with how many significant figures you're supposed to round to. I think 1 or 2 is fine. So this or 4.7, I guess. Yeah, that's it. So that's 4 good questions about scalars, vectors, SI base units, and uncertainties. Basically combining uncertainties. That's it. So, okay. And now we'll talk about a bit more on the philosophy of physical units. Right. So I get excited mostly for these parts where I'm going to go deeper and I'm going to go in. A little pre-warning here. Some of the stuff I might be saying and questioning may rock the boat a little bit and could be possible to give you an existential crisis almost, maybe. So I just want to pre-warn that because that's actually no joke. I'm going to be questioning a lot of the foundational things that are just taken as true here in physics. Not because I want to degrade physics, it's because I want physics to be the best it can possibly be, and I want to be a honest and authentic teacher and to get you to be the same in your own learning. Question things. I want you to question things. I don't want to be some teacher that just gives you shit and just says, okay, this is how it is, accept it, and just use it in an exam and that's it. No, we want to question these things and really think about them from scratch. So a little pre-warning, but I'm here, I'm doing this out of love. I'm doing this out of desire for people to open their mind and to understand. Okay, that being said, so what is a physical quantity? When you look around, even your room, you must notice that you can identify millions of things. You can identify millions of colors. You can identify millions of objects. You can label millions of things. You can label physical quantities as well. Like if we take something like this book here, just from this book, we could literally derive so much of physics. From this one book, this book has length, it has mass, it has volume, it has density, it has a speed and acceleration when you drop it. There's so many things that can come just from this simple black book, a simple object. And that's actually a remarkable thing, right? I mean, all of the physics, all of this crazy complex physics has all been derived in a room just like the one that you're sitting in right now. Amazing, no? Anyway, but the question is, what are these physical quantities? And do they even really exist? Physics is, in fact, a way of agreement. This thing has mass, right? We'd say that. Oh, it weighs, well, let's say, 100 grams. Like, yeah, it weighs 100 grams. Does it weigh 100 grams? Or is that something we're making up for a way to agree? Almost like think about 2 monkeys or something, just chilling, being like, do you feel this? You experience a feeling, which now we're calling mass or weight. But it's a way for us to agree on our experience. So I could be like, do you feel this? And you're like, yeah, I feel this. And then we quantify that and we say, okay, so this is a mass of 0.100 grams or whatever. So it's a way of agreement. But in actuality, do these things exist? You'd be like, well, yeah, they exist, man. Just go put it on a scale. Okay, well, who created the scale? We created the scale. Who created the numbers? We created the numbers. Who created the language of mass? And who created the language of weight? Who created the language of grams? These pointing things. We created all of it. So in actuality, I would say, and go out on a limb here, these things don't exist out of humanity, out of the human being's mind. but we use these things in physics because it's so useful for us to agree upon our experiences. I can tell you and explain to you that this thing is light. It weighs a certain mass, and that's a very powerful because it can allow us to agree on a physical quantity in our experience. This is a profound jump that we made, because we can connect our experiences together and agree upon them and then manipulate them. So that's really the play, the role that physics is using here in terms of physical quantities. We're using it as a form of agreement rather than an actual expression of truth. And so, just a little talk there about physical quantities. I'm going out on a limb here because when you bring it into your actual experience, you don't see mass, you don't see length, you don't experience these things. They are things that we have created, very powerful tools that we have created in order to manipulate and agree upon experience. So that's it. Hopefully you enjoyed that introduction here. Like, subscribe, and I'll see you later.